Artemis II is coming home from the moon right now, and its main rocket engines are completely dead. They won't fire again. For the entire multi-day journey across the vacuum, there will be no thrust, no propulsion. The spacecraft isn't broken. It is perfectly on course. It is simply falling, completely unpowered, hundreds of thousands of miles toward that blue marble. Navigating the void with dead engines is a calculated choice. It is an exercise in using the invisible architecture of space to survive. To understand why, you have to look at the harsh economics of mass. Every single pound of fuel you carry for the trip home is a pound of scientific equipment or life support you leave behind on the launch pad. It is the exact same math that strains terrestrial supply chains. Businesses constantly pay a heavy penalty to hold buffer stock on their shelves, just in case something goes wrong. This chart shows the sequential drain on capacity. Whether it is a warehouse or a rocket, holding insurance is expensive. An average business carries a 23% excess inventory margin to handle demand surprises. That is cash sitting completely dead. NASA looked at the mass limits for a deep space lunar return trip. They realized they could not afford that 23% insurance policy. To move massive payloads to the moon, you have to eliminate the contingency cost of the return trip entirely. You have to force the environment itself to do the heavy lifting. The entire mission relies on one violent expenditure of human propulsion, the translunar injection burn. That outward thrust lasts exactly 6 minutes, then shuts down. The timeline shifts forward to April 6, 2026. The spacecraft goes silent, and human control hands over to celestial mechanics. The capsule sweeps across the horizon, coming within exactly 4,066 miles of the lunar surface. Crossing that specific proximity threshold means the craft has officially entered the moon's gravitational sphere of influence. At this exact coordinate, the moon ceases to be a destination to look at. It becomes a massive, invisible tool to be used. This free return trajectory uses orbital positioning to replace active thrust. By slipping into the gravity well at the correct angle, the moon catches the spacecraft. Orbital momentum whips the capsule around the dark side, snapping it into an unpowered, straight line right back to Earth. This passive gravitational redirect does the exact same job as a multi-million-dollar thrust maneuver. By treating the solar system as a machine, NASA turned the largest obstacle in the sky into a free fuel pump. The math is celestial, but this was a strictly economic decision made at terrestrial consoles. The logic is highly leveraged. Every ounce of fuel saved on the homeward leg translates directly to an ounce of extra payload capacity on the way out. That exact margin of fuel savings dictates whether launching a complex lunar logistics mission is mathematically feasible or entirely impossible. Compare this foresight with an Earthbound distributor holding a $180,000 in dead stock. They bleed cash carrying buffer inventory because they do not know where the pull is coming from until the customer is already waiting. True efficiency does not come from installing a larger fuel tank. It comes from anticipating the exact pull of the system before you ever start moving. Large-scale logistics, whether in deep space or on a global highway, share these same physical constraints. Moving efficiently means moving past the need to fight nature with brute force. Gravity and the demand dynamics in our own businesses act as permanent, invisible infrastructure waiting to be utilized. Whether managing global supply chains or navigating the dark, you master the journey when you stop burning fuel and let geometry do the work.